Hello, Assalamualaikum warahmatullahi wabarakatuh, and good day to all the students and to all of you. So welcome back, guys. Okay, now we go for the part 3 of the chapter 3, gas power cycle. On the part 1, we already settled for the fundamental of the gas power cycle and gas turbine engine, and then we already emphasize our understanding about this gas turbine engine in the part 2. So we done several example, okay, and then now we go for part 3. So this part 3 basically will discuss about the actual cycle of the gas turbine engine, because in chapter 1 we discuss on the chapter 1 and chapter 2 is only cover for ideal cycle, but now for chapter 3 on part 3, so we will cover on the actual cycle of this power cycle. Okay, right. So deviation of the actual gas turbine cycle. Okay, so the actual gas turbine cycle differ from the ideal Brayton cycle. Okay, the actual work input to the compressor will be more, and the actual output from the turbine will be less because of this irreversibility. So what is irreversibility mean? So irreversibilities or losses of an ideal gas turbine, okay, can be determined by this figure. You look into as you can see for the TS diagram here, and then if you look here, so for the state 1 to state 2, okay, there's an ideal condition, which is state 1 and state 2S is an ideal condition. So which is at here, okay, you can see here, okay, so here, so this is the ideal condition, which is S to S will be equal to S1. So S is a entropy here, as well as this one, okay. So this one is going to be the ideal condition, okay. 3 S3 is equal to S4S, okay. But in the actual cycle of the gas turbine engine, so in the actual cycle of gas turbine engine, basically the compressor will produce more work, okay, because at the first place is that compressor must be the overspec so that it can achieve the desired pressure that you want. Because in ideal condition, that means you produce less work, but you got the desired pressure. But in actual, they will produce more, required more power for the compressor, and then the output from the turbine also more or less as compared to the ideal one. So here, that's why we have differ for the actual value. So we have the 2A and 4A. So 2A means the actual value, right? So that means 2 actual lah, actual. And then for 4A will be 4 actual. Okay, right. So these two things contribute to the actual gas turbine cycle. Okay, so as you can see here, so these are different between these two. So here we have one value, and this one is one value. So here, okay, is okay, one value, and then okay, this is one value here, and then one more is here, right? So they have two different values, right? So two different values here. Okay, so you have here and here. So this one we call it W compressor ideal. Okay, and then for this one, okay, right, for this one we call it W compressor actual. Okay, so W compressor actual, right? Okay, okay. So then also happen to here, okay, also happen to the turbine, okay. For the turbine, basically here, so we have here, so here is going to be a value, and then another value is come out from here. right? So since this one, okay, at this stage, we call it W turbine actual, and at here, we call it W turbine ideal. Okay? So here is ideal turbine work, this is actual turbine work, here is actual actual compressor work, and here is ideal compressor work. Okay, right. So here, so the frictional effects within the compressor and turbine cause the working fluid increase in specific entropy. So due to this friction also, they will cause the pressure drop when the working fluid is passed through the heat. So because they have some friction, you can imagine that the compressor is rotating, and then the airflow inside the compressor will interact with the turbine blade or the compressor blade, so they will occur the friction. So this friction basically will reduce the pressure. Okay, you can imagine that when you basically play when you run. So when you run, okay, when you drive a car or drive a motorcycle, at the ideal condition, when your tire have a good amount of air, so you can go very smoothly. You can move very smoothly. But what happens if this your tire, have very less of the amount of air inside the tire? So of course you will go slow, but you need more power to press that as compared to the ideal air inside the tire. So you can see that. So that means if the air in the tire is lower, so that means the contact area between the tire and the road is much larger. So they will increase the friction. So this happens the compressor and turbine. Okay, and then the effect of the irreversibilities in the turbine and compressor are important, and then the work developed by the turbine and will be decreased, right? Because in ideal case, you can produce the work here, right? So here, you dapat W turbine before this kan. So W turbine ideal, right? Okay, but the temperature is getting lower, right? So that means at here is going to be W turbine actual. So it's getting lower as compared to this one. Okay, right? And then at the same here, okay, the compressor work for the ideal case will be lower as compared to the actual one. So the actual one, W actual compressor, may more higher. That's why this is the effect of the irreversibility and the losses. Okay, boleh? Okay, right. So due to these losses, so we can basically represent in terms of the compressor efficiency, or we call it isentropic efficiency for the compressor. And then as well as turbine, we have the turbine efficiency. So we can call it as an isentropic turbine efficiency for the turbine part. Okay. So this isentropic efficiency for the compressor can be determined by the ratio between this one and this one. Okay, right? So here, okay, and here, right? The ratio between the ideal work and the actual work. So that's why here ideal work divided by actual work. So T2S minus T1, okay, because entropy for the compressor actually is equal to W compressor ideal, okay, ideal divided by W compressor actual. So from here is M dot Cp T to S minus T1, because T ideal is between T to S and T1. And then here is M dot Cp T2 actual minus T1. So you can simplify that. Then the result will be 2S minus T1 divided by T2 actual minus T1. So this is going to be your isentropic efficiency for the compressor. Okay, right? but it different to the turbine. Okay, so the turbine. So here is going to be your actual W actual, and here is going to be your W ideal. So the small amount divided by the larger amount. So that's why here is W turbine actual divide W turbine ideal. So from the formulation M dot Cp T3 minus T4 actual divided by M dot Cp T3 minus T4S. Right? So this one can be simplified. So the result will be like this one. T4 actual divided by this one. Okay. So this one we call it isentropic efficiency. Okay. Isentropic efficiency for turbine. Okay, clear guys. Alright. So that means in actual condition, so the compressor will produce more work. Need to produce more work. Okay. So that's why we have the isentropic efficiency for the compressor as well as turbine. The turbine output is much lower as compared to the ideal one. Okay, due to the losses. Okay, because why? Why the compressor need to push more work? Because compressor, the ideal case basically if compressor can produce less work and can achieve this kind of pressure, but in actual they need to produce more power in order to find this pressure also. So that's why compressor need to produce more power, and then this difference is represented in terms of the efficiency. But as compared to the turbine, okay, turbine and the case should be produce this power. Okay, but in actual they cannot produce this power, and then they will produce less power. So this difference between the actual and the ideal will represent for the efficiency for the turbine. Okay, clear? So when you got the value of actual for each value for T2 actual and T4 actual, so that if you want to calculate the W compressor, there will be the formulation is you use T2 actual minus T1, right? So before this you use T2 ideal, right? And then it's similar with the turbine. So W turbine is M dot Cp T3 minus T4 actual. So this is going to be the work for turbine. Alright guys, I hope you understand. So now we try to do some example. Okay. So a simple Brayton cycle using air as the working fluid with a pressure ratio of 10. And then the minimum and maximum temperature in the cycle are 295 Kelvin and 1240 Kelvin. Assuming that the isentropic efficiency of 83% for the compressor and 87% for the turbine. So you have to calculate the air temperature at the turbine exit, the network output, and the thermal efficiency. Okay. So the keyword here actually is this one. Okay. The keyword here is actually this one. Isentropic efficiency. So when you find the value of isentropic efficiency, that means this value is going to be the actual cycle. So this one is actual cycle. So this is the key. The key one, the first one is isentropic efficiency. Okay, we try to solve this. Okay, so the first one, okay. So we got this one, isentropic efficiency. Okay. Right. So this one is actually is an actual cycle. Okay, like I explained to you before in the ideal cycle. So before you start, you have to develop your TS diagram. Okay, so for TS diagram, so this is a basic cycle for TS diagram. So 1, 2S, 3, 4S, and then they give you the value of isentropic efficiency. That means there will be 2 actual and for actual. Okay, so you have to find all each state value, which is state 1, state 2s, state 2a, the value of 3, 4s, and 4a as well. Okay, right. So in the question, they give you the value of pressure ratio Rp, which is P2 over P1 is equal to 10. Okay, right. And then in the questions, it also gives you about the value of T1. So T1 is 295 Kelvin. Okay, 295 Kelvin. And then they also give you the value of T3, which is 1240 Kelvin. Okay, right. Okay, guys, and then they give you the isentropic efficiency for the compressor, 83%. Okay, and then they also give you the value of isentropic efficiency for the turbine, which is 87%. So now you do state by state. Start with state 1. Start with state 1. So for the state 1, value of T1 is given, which is 295. So it's okay, right? It's okay. And then you can proceed to state 2. Right? For the state 2, okay, you can, because this process of isentropic compression, okay, so you can use isentropic efficiency, isentropic relationship, which is T2F over T1 equal to P2 over P1, K minus 1 divided by K. So this one is equal to Rp K minus 1 divided by K. So T2S actually is equal to T1, 295 Kelvin, times by the Rp. So Rp is equal to 10, 1.4 minus 1 divided by 1.4. So from here, you get the value of T2S is equal to 569, okay, 569.556. Okay, right. And then, so to find the value of T1, T2F, now you have to find the value of T2 actual. So T2 actual can be used, it can be found by isentropic efficiency for the compressor, because the isentropic efficiency for the compressor, okay, is W compressor ideal divided by W compressor actual, whereby the value, okay, actually is, the value is okay, so okay, equal to m dot cp T2s minus T1 divided by m dot cp T2 actual minus T1. So this one can be cancelled. So you got T2s minus T1 divided by T2 actual minus T1. So you can apply the values. So isentropic efficiency for the compressor is 0.83 equal to T2s is 569.556 minus the value of T1. So T1 is 295, okay, divided by T2 actual minus T1 is 295. So from here, you can find the value of T2 actual is 625.7902. Okay, guys. Okay, I hope you can understand. Okay, right. So T2 actual must, the value must be higher compared to T2S. That's the first principle. Because from here, you also know, T2S is lower than T2 actual. Alright, now you go for the state 3. Okay, for the state 3, it's a process of constant pressure, okay, heat addition, Okay. So from here, so the value of T3 is given 1240 Kelvin. Okay, settle and then you go for the state 4. State 4 is a process of isentropic expansion. Okay, isentropic expansion. So you can use isentropic relationship, which is in this case is T3 over T4S equal to P3 over P4 powered by K minus 1 divided by K. And then this one also equal to, basically P3 equal to P2 divided by P1. Okay, K minus 1 divided by K. And then this one also equal to RP K1 minus K. Divided by K. Okay, so the value of T4S here actually is equal to T3. So T3 is 1240 divided by the RP is 10 powered by 1.4 divided minus 1 divided by 1.4. Then you get the value of T4S is 642. 642.2549. 0.2549 Kelvin. Okay. Okay guys. Okay. Alright. And then similarly, you also get the value of T4S. Now you have to find the value of T4 actual using the isentropic efficiency for the turbine. So isentropic efficiency for the turbine actually is equal to W turbine actual divide W turbine ideal, right? So it's quite differ with the compressor work and compressor efficiency. So this one m dot Cp, okay, T3 minus T4 actual divided by m dot Cp, T3 minus T4s. So this one can be cancelled. And now thermal efficiency for the turbine will be T3 minus T4 actual divided by T3 minus T4s. Okay, so guys, you can put the values. Okay, you can put the values. So 0.87. So 0.87 is equal to T3. T3 is given by 1240. So 1240 minus T4 actual. Okay, divided by 1240 minus T4S. So T4S actually is equal to T4 equal to 642. Okay, 0.2549. 2549. Then from here you will get the value of T4 actual. So T4 actual is equal to 719. Okay, 719.9617 Kelvin. Okay, clear. Alright, so now you already found all the properties. Now you can answer the first question. The first question actually is require you to calculate the air at the turbine exit. So you already found that. So T temperature turbine exit. So this one actually is equal to T4 actual lah. Which is 719.9617 Kelvin. Okay. And then question number 2, we required us to calculate the value of the W net. The network output. So W net. So W net basically is W turbine minus W compressor. So from here, W turbine can be determined by m dot Cp T3 minus T4 actual. So this doesn't give you the value of mass flow rate. So Cp T3 minus T4 actual. So from here we have 1.005. T3 is 1240 minus T4 actual. So T4 actual is 719.9617. So from here, you can get the value of the W turbine, which is 522.6385. 522.8365. Okay, guys. Okay. 522.63. Sorry, 6385. Sorry. Hang on. Okay. So you will get the value of the W turbine, which is 522.6385. 6385. 6385. Okay. Kilojoule per kg. Alright. Okay, guys. And then you can proceed to calculate W compressor. So you have to use the actual value also. Cp T2 actual minus T1. So from here we have Cp T2 actual minus T1. So 1.005 times by the T2 actual. So T2 actual is 625.7. 625.7902. So T1 is equal to 295. So from here, you will get the value of W compressor. Okay. W compressor is equal to 332. Okay. 0.4441. 4441 kilojoule per kg. Right, guys. Right. Okay. Okay. I think you understand. Okay. Right. Okay. Now you can proceed to calculate W net. So W net is W turbine minus W compressor. So from here, so W turbine is 522.6385 minus 332.4441. So W net here, we can find the value of net is 190.1944 kilojoule over kg. Okay, the last question is, we have to find the value of thermal efficiency, right? Thermal efficiency is W net over Q in. So W net is already found, which is 190.1944. And then the value of Q in is m dot Cp T3 minus T2 actual. Okay, so Cp T3 minus T2 actual. So 1.005. So T3 actually is equal to 1240. Okay, 1240 minus T2 actual. So T2 actual is 625. Okay, T2 actual 625.7902. So you can find the value of Q in actually is equal to okay. So 617.281 kilojoule per kg. Okay, guys. Okay, once you find the value of Q in, okay, when you find the value of Q in, then you can proceed to calculate the value of thermal efficiency. So here, thermal efficiency is W net 190.1944 divided by 617.281. So from here, you will find the value of thermal efficiency is 0.308. So it's different between thermal efficiency and also the isentropic efficiency, right? Different. The isentropic efficiency actually is the efficiency for the component, and thermal efficiency is efficiency for the overall. Okay, overall performance. Okay, guys, and then we can proceed to another question, example 3.6. So air enter the compressor of an air standard Brayton cycle at 100 kilopascal 300 Kelvin, and then they give you the value of volumetric flow rate of 5 meter cubic per second. And then the compressor pressure ratio is 10, and then the turbine inlet temperature is 1400 Kelvin, and the turbine and compressor each have the isentropic efficiency for 80%. So that means from here, they have the isentropic efficiency. That means this is going to be the actual cycle. Okay, actual cycle. So you have to calculate the thermal efficiency, back work ratio, and net power developed. Okay, guys. So since you know that this is actual cycle, so start your calculation with the TS diagram. Okay. So start your calculation with the TS diagram. So here 1 is 2 into S, 3 in 4S. So here is 2 actual, and here we have 4 actual. So in this question, they give you the value of P1. Okay, so P1 is given, which is 100 kilopascal. Okay, 100 kilopascal. And then the value of T1 is given also, which is 300 Kelvin. Okay. Okay, right, 300 Kelvin. And then they give you the value of volume flow rate, V1, which is 5 meter cubic per second. Okay, guys. And then at the same time, the value of RP equal to P2 over P1, which is 10 in this case. Okay. And then T3, okay, so T3 is equal to 1400 Kelvin. Okay. And then the value of isentropic efficiency, okay, for compressor, and also equal to isentropic efficiency for the turbine, which is 80%. Okay, guys. Okay, so now we do state by state. Okay, so start with state 1. Okay, start with state 1. So state 1, P1 is given 100 kilopascal. Okay, and then T1 also given by 300 Kelvin. And then V1 actually is equal to 5 meter cubic per second. Okay, and then you go for the state 2. State 2 is an isentropic compression. So we have here T2S over T1 equal to P2 over P1 powered by K minus 1 divided by K. Also this one is RP K minus 1 divided by K. So T2S actually is equal to T1. So T1 is 300 Kelvin and the RP is 10. Okay. 1.4 minus 1 divided by 1.4. And then the value of T2S can be found by 579.2095. 2095. Okay, guys. Don't forget about unit. So unit will be important. And then since you find the value of T2S, now you have to find the value of T2 actual. So it can be found by using the formulation of isentropic efficiency for the compressor, which is W compressor ideal divided by W compressor actual. Okay. So right. So here thermal efficiency, okay, isentropic efficiency for the compressor is m dot Cp T2S minus T1 divided by m dot Cp T2 actual minus T1. So this one can be cancelled. So they will left you in terms of T2S minus T1 divided by T2 actual minus T1. The isentropic efficiency for the compressor is given by 80%. So here is 0.8. So T2S have been calculated, which is 579.2095. The value of T1 is given 300 Kelvin. Okay, divide by T2 actual minus 300, and from here you will get the value of T2 actual, which is T2 actual is 649, 0.0116 Kelvin. Yes. Okay, and then you go for the state 3. Okay, you go for the state 3. It's a process of constant pressure heat addition. So T3 is given by 1400 Kelvin, and then you go for the state 4. State 4 is a isentropic expansion. Okay, so you can use isentropic relationship. T3 over T4 is equal to P3 over P4 powered by K minus 1 divided by K. So this one also equal to P2 over P1, K minus 1 divided by K. So this one also equal to the ratio. Okay. Alright, so the value of T4S can be found by, so T3 is 1400 Kelvin divided by our pressure ratio. So pressure ratio is 10. Okay, 1.4 minus 1 divided by 1.4. So from here, the value of T4S actually is equal to 725, okay, 0.1265. So 1265 Kelvin. Alright, okay. And then, so you find the value of 4S. Now you have to find the value of 4 actual. So for actual can be found by using the formula of isentropic efficiency for the turbine, which is this one is W turbine actual divided by W turbine ideal. Okay, which in this case is M dot Cp T3 minus T4 actual divided by M dot Cp T3 minus T4 S. So this one can be cancelled. Okay, so it will left you only the temperature. So T3 minus T4 actual divided by T3 minus T4. So you put the values. Put the values. So here is 0.8. So T3 is given by 1400. Okay, 1400. T4 actual divided by 1400 minus T4S. So T4S is 725.1265. Okay, right? So eventually you will get the value of T4 actual, which is 860, okay, 0.1012, okay, 1012 Kelvin. Okay guys, so you got all the purposes. Now you can start your calculation. Okay, the first question is, it requires you to calculate the value of thermal efficiency. So if you look in the question, thermal efficiency of the cycle. So thermal efficiency of the cycle actually is equal to W net over Q in. So calculate W net. So in this case, okay, the W net can be calculated by W turbine minus W compressor. Okay, and then W turbine can be calculated by M dot Cp T3 minus T4 actual. And then in this case, okay, they give you the value of volume flow rate. So that means you have to find the value of the mass flow rate. So the mass flow rate basically can be found by using the formula of volume flow rate. divided by specific volume. Okay, so this one actually is the volume flow rate. Okay, and this one is going to be your specific volume. Okay guys, so now the value of the volume flow rate, this one has been given 5 meter cubic per second. Now you have to find the value of specific volume. So volume can be found by using this formulation. You can use ideal gas law, okay, which is P1 equal to M3 RT1. Okay, ada M tadi. So V1 here is RT1 divided by P1. So RT1 here actually is a constant which is 0.287 and T1 is given by 300 Kelvin, okay, and the P1 is also given 100 kilo Pascal. Now you can find the value of V1 here is 0.861. Okay, this is constant, this is constant, so you use the 0.287. So now you can find the value of mass flow rate. So the mass flow rate is volume flow rate divided by specific volume. So 5, okay, meter cubic per second is divided by 0.861. Then you can find the value of mass flow rate is 5.81 kilogram per second. Right. And then when you find the value of mass flow rate, then you can find the value of W turbine. So W turbine is the mass flow rate, Cp T3 minus T4 actual. So the mass flow rate is 5.81 divided by Cp 1.005. T3 is given by 1400 Kelvin, okay, minus T4 actual, we already found that, so T4 actual is 860, okay, 0.1112, okay, right. Then eventually you will get the value of the 1012. So then eventually you get the value of W turbine will be 3152, okay, 0.496. Okay guys. Okay. And then so proceed now to calculate W compressor is mass flow rate Cp T2 actual minus T1. The mass flow rate is 5.81. Cp is 1.005. T2 actual is 649, okay, 0.0116 minus T1 is 300, okay. Now W compressor you will get 2037.896 kilowatt. Okay. Now W net you can find by W turbine minus W compressor. So W turbine here is 3152.496 divided by W compressor is not divide, minus 2037.896. Then eventually you will get the value of W net will be 114.6. Okay, right. Okay, so you get the value of W net. Then you proceed to calculate the value of Q in. So Q in is M dot Cp T3 minus T2 actual So M dot is 5.81. CP is 1.005. T3 is 1400, and T2 actual is 649. Okay, 649.0116, and then you get the value of Q in, which is 4385. Okay, 0.059 kilowatt. Okay, now you get the value of W net, you get the value of Q in, then you can proceed to calculate thermal efficiency. If W net over Q in, over Q in, so W net is 1114.6 divided by 4385.059. So from here you can get the value of thermal efficiency is equal to 0.254. You guys please check. And then question number 2, they request you to calculate the value of backward ratio. So backward ratio is just simply the ratio between W compressor divided by W turbine. So W compressor is 2037.896 divided by W turbine is 3152.496. So backward ratio actually is equal to 0.6464. Okay. Alright, nice number. Okay, and then question number 3, they request you the calculation for the network power developed. So WNet. So WNet ni you already calculated, which is 1114.6 kilowatt. Okay guys. Okay. So this is some example that you can use as your basis to calculate the actual gas turbine cycle. So I think for the part 3 is ended here. So we will see in the part 4, guys. Okay, after this. So part 4. So part 4 is more into the actual cycle with the regeneration. So that means the method how you try to increase the thermal efficiency values. Okay, guys. Until next chapter. So we will meet again in part 4. Thank you, guys. Okay, I hope this all will help you to understand. Okay, thank you, guys. See you on part 4. Okay.